All right. Morning, everyone. Today we'll finish stereochemistry of chemical reactions and then start chapter 8. Hopefully, we can get a little bit into that. So I wanted to talk. So up until this point, we've talked about this idea that achiral reagents plus achiral starting materials always leads to racemic products, okay? If you're generating stereocenters. And someone correct me if I'm wrong, but I think we left off with an example where we now had a stereocenter in our molecule, and we were talking about hydroboration. So that's where I want to start here. So okay, so we want to consider the case where our starting material bears a stereocenter. I've drawn it there. So it's a single enantiomer. I've only drawn one enantiomer of the compound, and I haven't written the plus minus sign. So the plus minus sign would tell me that I have a racemic mixture. If I leave that out, the implication is that I have a single enantiomer. And so we have this compound with the specific configuration at the sort of C star up there, okay? So we're going to do the hydroboration, and then we're going to do the oxidation. And we know that the boron is going to attach to the less hindered carbon. The B and the H come in on the same side, and the oxidation of the alkyl borane proceeds with retention of configuration. So the OH ends up on the same side as the hydrogen from the borane. And so as before, we said, okay, we could attack either face of the molecule. We're going to do the same thing here. Okay, and so there are the two possible products. And so the question I put to you is, what is the stereochemical relationship between these two products?
Diastereomers.
Great. Yeah, they're diastereomers. So they're stereoisomers, but they're not non-superimposable mirror images. They're not enantiomers. And so if we look at this, if we want to sort of unpack that a little bit, you can say, okay, just considering these two stereocenters that I boxed in green, we've inverted both of them, moving between the two products, but the one circled in blue there remains constant. So in order to have an enantiomer, you have to invert all the stereocenters. And so we're not doing that. And so we're making diastereomers, okay? And so the very interesting, let me just close my door here. The interesting consequence of this is that because they're diastereomers, they don't have, in principle, they don't have the same energy, okay? And the transition states that lead to these different products are going to be diastereomeric. So previously we've talked about enantiomeric transition states. So transition states that are non-superimposable mirror images of each other, okay? In this case, the transition states are diastereomeric. So let me put this on a reaction energy diagram. Okay, so there's our alkene plus borane. And let's call this product on the left, just so I don't have to rewrite everything, A, and we'll call the one on the right B. Okay, and so product A is going to be somewhere down here. And then product B will be somewhere over here. And I'm not trying to imply anything between the relative energies of the two products. So they're not equal. I don't know which one's higher or lower. What we're really concerned about are the transition states. So effectively just ignore the vertical positions of A and B. What does the transition state leading to A look like? Well, something like this. So you're starting alkene with the methyl group, and your borane is coming in from the bottom face. All right, yeah, so let me just draw that. So the boron's coming in from the bottom face. That leads to the hydride on the bottom, and then ultimately the hydroxyl group on the bottom. And so this is, we'll call this A double dagger, okay? And there's some energy associated with it. And then the transition state to get to B is similar, except the borane's on the top. So I'll draw that over here. And you've basically got something that looks like this. Okay, so this is B double dagger, okay? And we can associate some sort of energy with that, all right? And I'll just put the energy there for sake of argument. It might be lower, it might be higher. I think it's probably higher. The point is that, the important point is that the stereochemical relationship between these two transition states is that they are, in fact, diastereomers. They are non-superimposable. They are not enantiomers. They are not non-superimposable mirror images of each other. They are just stereoisomers. And so they're going to have different energies. And that means that the top of the reaction pathway to get to them is going to be at different heights. And so the activation energy then is going to be different. Okay, so the delta G double dagger A does not equal delta G double dagger B. Okay, previously we said when we had enantiomeric transition states that those delta G's were identical, right? The activation energy to get to those transition states are identical. because they're enantiomeric, they have the same energy, okay? Now we've gone to diastereomers, and just like ground state stable molecules, diastereomers have different energies. So do diastereomeric transition states, okay? And I just want to add one qualifier, which is that, like I said, I don't know which one is actually in practice higher or lower. That's not so important. The take-home message is that they are different. And because the delta G double daggers are different, you're going to have different rates of formation of each product. And so these aren't going to be formed in an equal amount, okay? So I'll pause there for a second and take questions.
So just to clarify, we wouldn't ever be expected to like guess which transition state would be more stable, right? Or
no, not at this point. Yeah, if you go on to sort of advanced organic, you'll have to learn this. But no, the answer right now is no. All right. If there's no questions, let me just show you a really cool example of this. So, you know, organic chemistry is an old subject, but, you know, a lot of this stuff, this idea of like diastereomeric transition states and, you know, things like that really weren't well understood until the 70s. And you don't need to copy this down. This is a famous molecule known as Menensin. Okay, so this is a molecule known as Menensin. We call this a polyether antibiotic. It has antimicrobial properties. These things tend to bind metals. If you know what a crown ether is, this is essentially a crown ether in a tuxedo. And you know, back in the day, it was not. Nowadays, this would be a sort of a more, you know, we'd almost characterize this as a boring target for synthesis because it's the chemistry is sophisticated enough that it's fairly straightforward to make. But in the 70s, this was sort of at the forefront, right on the edges of what was possible. And there were several groups that worked on this molecule, and Yoshito Kishi at Harvard was one of the first people to finish it. And one of the key steps in that synthetic route involved a hydroboration, where we're making use of this idea of sort of non-equal energies between transition states for the addition of borane to an alkene. So I just want to highlight that. I would just say that Kishi's one of the greats of synthetic organic chemistry. He was actually on my thesis committee. He made molecules in like the 70s and 80s that people were still getting tenure on in the 2000s at, top places like Stanford and other places. So he was way ahead of his time. Okay, so this is a substrate that Kishi prepared. Got an olefin. We're going to do a hydroboration. Okay. This carbon here is coming out at you, and I've sort of used that sort of triangular representation to show it. If you wanted to look at this flat, it would look something like this. Okay, so question is, how many stereocenters in this molecule? Asymmetric stereocenters. Ghana, what do you think?
For now, I only see one for certain.
Yeah. Yeah, there's one, this one, right? That's what you're thinking of?
Yeah.
Yeah, exactly. Yeah, don't let the complexity throw you off. It's that there's one stereocenter here. Okay, so the point is we've got one stereocenter. We have an existing stereocenter. I haven't drawn a plus minus, so it's not a racemic mixture. It's a single enantiomer. Indeed, it was a single enantiomer when they made it. We're going to treat this with borane, and the question is, what's the stereochemical outcome? Okay, and to sort of understand that, let's first think about what we know about hydroboration to help to kind of like winnow down the possibilities. So boron's going to attach to the less substituted carbon of the alkene. So that's going to be this guy highlighted in green there. Okay, so that's great. We know that it goes through a concerted four-center transition state. So B and H end up on the same side. It's a syn addition. We said before that's a little trickier to see in acyclic alkenes, but you can still kind of, you still need to think about it as you're working the mechanism. And so what's left is really the facial selectivity and the addition of borane to the olefin. So I can come in from the top or I can come in from the bottom, right? And let me just draw those two transition states. So Okay. And so those are the two transition states for the addition of borane to either face of this alkene. Okay. The stereochemical relationship between those two transition states is that they're diastereomers. Okay. So I have a single configuration at this position, right? And then I've inverted the configurations at the carbons of the alkenes. And so I haven't changed all of the stereocenters. So I've made a diastereomer. Does anyone want to venture a guess as to which is better? And I don't expect you to know this, but if you have an idea and you're comfortable throwing it out there, go ahead. We got a 50-50 chance.
Would it be the bottom one?
Yeah, why?
I guess it has less to interfere with it when it's on the bottom.
Exactly. Excellent. Yeah, exactly. It's just non-bonded interaction. So this is something you would learn about in sort of the next class if you ever take it. But basically, yes, the bottom face is less hindered. Okay. And so this conformation here with the hydrogen in plane with the alkene is the lowest energy conformation of the molecule that sticks this heterocycle. This is known as a furan that sticks the furan up and the methyl group down, okay, with respect to the plane of the alkene. And the bottom transition state where the boron is approaching syn to the alkene, syn to the methyl, is just less hindered. There's just less for it to bump into. And so it turns out, I'm not going to spend time drawing the products, but what you end up with is a ratio of about 8-to-1 in favoring the bottom. Okay. And so I actually should draw the product to make a point here. I'm going to try and do this on the next page without getting jumbled. So if we have okay, so this product is formed with about 8-to-1 selectivity with respect to its diastereomer, where I've inverted the two centers here, okay? So why is this a powerful reaction? This is a powerful reaction because I've used one stereocenter. That stereocenter, put the hydrogen in there. Yeah, all right, this is kind of messed up, but I've used this stereocenter that we had in our starting material to control the selectivity in the formation of two more stereocenters. Do you see what's happening? And so that is we call that diastereo control, substrate control. It's very important because you don't want to just be making random mixtures of stereoisomers, right? You want to have a controlled synthetic route where you're basically dialing in every stereocenter exactly the way you want it. That's the ideal, at least, right? And so what's powerful about the hydroboration in this context is that because I add hydrogen, I add a substituent to each carbon of the alkene, okay? And the substitution of the alkene is such that when I do that addition, I generate two new stereocenters. I can control those with that sort of distant, that green stereocenter, the center I marked in green there, okay? And so at the time that this is common now, any of my students could lead you to the same answer, but at the time that Kishi did this was like new. This was like, holy cow, we didn't know that we could, control stereochemistry in this way. And so very powerful transformation and allowed them to make one of the key substructures in the target. So hopefully you find that interesting. All right, so I just want to say a couple more things about stereochemistry, and then we'll get to chapter 8. So So up until this point, we've talked about reactions where you've had a specific stereochemical outcome in terms of how the reagents are added to the alkene. So dibromination, you make a bromonium ion, bromide comes in from the back, right? And so we were calling that an anti-addition because the bromines end up on opposite sides of the alkene. Hydroboration, like we just covered, syn addition, the B and the H come in on the same side, and then the OH, the oxidation proceeds with retention of stereochemistry, so that's a syn addition. The final class are basically non-selective reactions, and can illustrate it, go back to an old simple example. So methyl cyclohexene plus HBr. First step, protonation, bang, get to the carbocation. Okay, plus Br minus, right? And we know that, let me do this. Let me just blue this hydrogen so we can keep track of it. Obviously, in reality, it would get lost. But let's say that blue hydrogen comes in from the top face. And so you end up with that carbocation. The question is, what side does the bromide come in and attack? And if you want to look at this carbocation with perspective, we know that they are planar. And it would look something like that, right? And so there's equal probability that bromide's going to attack from the top or the bottom. And so the products that I would get would be that plus that. And again, we're hypothetically, if I could color my atoms, in HBr, we're going to color that hydrogen blue so we can follow it. Obviously, we can't in reality. But the point is that in the product, in one product, you've got bromine and the new hydrogen on the same side. In the other product, they're on the opposite side. And so this is what we would characterize as a non-selective addition to an alkene. So the carbocation has no memory or does not know where the hydrogen came in from when you protonated the alkene. All it knows is that it's symmetrical. It's got an equal distribution of that empty 2p orbital on either side. And so there's an equal probability you're going to attack. And so on either side. So this is a non-selective addition. Okay. And I give you one from the exam that was kind of built into that little bonus. So.
Wait, I'm so sorry. Do you mind going back for a second?
Yeah.
Thank you. Okay, great. Thanks.
That's it? Okay. So on the exam, we had methyl cyclohexene plus HBr and peroxides. Okay. And I'm not going to go through the whole mechanism. I just want to draw that first radical intermediate. So we'll distribute a key soon. So today, so you can look at the mechanism there if you want. But the key intermediate is this radical, right? And I drew bromide coming in from the top face. but it's equally likely that you generate the bromide coming in from the bottom face, right? And just like carbocations, the radical is sp2 hybridized. And so in the next step, you're going to generate a mixture of compounds where you've got hydrogen coming in the same side as the bromine and hydrogen coming in on the opposite side. So and then the same thing over here. Okay, so again, you don't need to necessarily copy this down. You'll have it in the key. But the point is that the facial selectivity with respect to addition, with the facial selectivity of addition of that hydrogen atom to the radical with respect to the bromide, it's non-selective. And so you get addition to the top or the bottom. And so you get a mixture of diastereomers, and then each of those is formed as a racemate. Okay, so all this is to say is that, you know, you can certainly memorize, you know, this gives syn, this gives anti, this is non-selective. The better way to do it, though, is just to get these mechanisms down cold. And so when you're confronted with a question like this, you know, you can work through the mechanism and reason your way to the correct answer. Okay. Any questions on that? Going to get my shot tomorrow. Both my wife and I are going. We're going to go at 9:45. It's, man, what a relief. Hope you guys can all get vaccinated soon. All right, so we're going to start chapter 8 then. I don't know which vaccine. I'm hoping it's the Moderna one, although, you know, they're all pretty similar, but the Moderna one seems to be slightly more effective than the Pfizer, and then the J&J. The J&J's will keep you out of the hospital, basically, is my analysis. It's not as effective against the sort of low grade infections, you know, where you get flu-like symptoms, but it will keep you out of the hospital, which is the most important thing. So, but then we're going to take our daughter.
We're all getting Pfizer tomorrow.
Are you? Is it on West Campus?
Yeah.
Pfizer.
They have
What time
like
are you guys
a
going?
calendar. 9:15.
Oh, I'll see you there. We're at 9:45.
I think like literally half of us are within the hour.
Awesome. So our daughter was born at the end of June last year. She hasn't met any of her family save for her grandparents, who came and visited once, and like it was like super awkward because they had to do masks and everything. So we're like, all right, we're going to take her to Illinois after we get vaccinated to see family. But then it's like half of our extended family has decided that they're not getting vaccinated. And I'm like, you guys are absolutely insane. That's a personal decision. If you don't want to get vaccinated, that's fine. That's a personal decision. But no, not holding the baby. Like, there's no way, you know, because we don't know what these things do to kids. And like, it's just, there's too many unanswered questions. So anyway, it's kind of not your problem, but bracing for some family awkwardness when we go out there. All right, so let me just keep going here. So chapter 8, intermolecular interactions. There's a lot to do about nomenclature in the chapter. Don't need to worry about it. I want to talk about the 3 types of interactions that are important. And there are others, but this is like 99% of it, okay? And so you probably have seen all of them. Okay. The 3 that you need to understand are London dispersion forces, AKA van der Waal interactions, dipole-dipole interactions, and hydrogen bonding, okay? And it's very important that you understand these. And the strength of these interactions generally increases in that order. So and so I'll start talking about the London dispersion interactions, and I just refer you to figure 8.3 for a very good schematic, a better one than what I'm going to give you, a schematic of this. Basically, you know, we draw these molecules as lines and wedges and sticks. And of course, that helps us think about them. But, you know, we omit a lot of details because it's just too complicated to think about everything at once. One of the things that we omit is that these things are just clouds of electrons, right? There's electrons in orbitals around the nuclei, and they combine to just make these clouds that are effectively molecules. And so if we think about it from that perspective, we can say, let's draw like pentane, okay? You can think about pentane as basically this like cloud of electron density, okay? And normally, you know, averaged over time, that electron density is sort of evenly distributed around the molecule, okay? But that's averaged over time. In fact, at any given instant, the electron density is not evenly distributed. It's kind of like sloshing around. You know, you can think about it like, you know, water in a cooler, right? Just kind of like slopping around the backbone of the molecule. And of course, we don't ever have just one molecule that we're thinking about. We've always got, you know, if we're in the liquid phase, a solution of them, you know. And so this sloshing of the electron density tends to kind of get in sync. And so, in other words, the molecules all sort of slosh in the same direction at the same time, okay? And so what we say is that you get some temporary polarization of the electron density. And so, for example, if the electron density shifts to the top here of this top molecule, that would leave this electron poor, right? And then this one is going to shift to the top, and this is electron poor down here, okay? And so this interaction, this plus minus interaction, is stabilizing, okay? And so they all kind of move together. You know, if you had to use the cooler now, like if you had this cooler filled with water, think about it like this, and you dropped a bunch of like, you know, rubber balls on there that floated, and you started to like shake it around, you know, they'd all kind of move in the same direction. And that's sort of what's happening with the electron density in a solution of a given molecule. It's all kind of sloshing around in the same direction at the same time. And the reason is that you get these transient polarizations where you can get delta plus next to delta minus, and that's anytime you bring opposite charges together, that's stabilizing. So, you know, it might seem counterintuitive, but in fact, it's a lower energy state to be sort of inducing these transient dipoles rather than just sitting absolutely static. And so that's a London dispersion interaction. And as you might gather from the way I've drawn it, the significance of this interaction is sort of roughly proportional to the surface area of the molecule. So molecules that are extended, like N-pentane, have stronger London dispersion interactions than those that don't, such as neopentane, which is basically this guy. And that's reflected in the boiling points. And so the boiling point of neopentane is much lower than pentane. I think it's even a gas at room temperature. All right, so then the next one are dipole-dipole interactions, which are typically stronger. And so, for example, when you have fluoromethane, right, we know that fluorine being very electronegative is going to pull electron density in the CF bonding orbital towards it. And so we can represent that with a dipole, okay? And just like with the London dispersion forces, if I can get this to align with another molecule in such a way that it puts opposite charges together, that's stabilizing. So let me draw this with another representation. So delta minus delta plus. And then you could imagine if you had another molecule in solution, it would orient approximately in this manner. Okay, and so that is, excuse me, stabilizing. So London dispersion, dipole-dipole, and then the most important one are hydrogen bonding interactions. And anytime you have a hydrogen attached to fluorine, oxygen, or nitrogen, it is potentially what we call a hydrogen bond donor. And so this OH group would be considered a donor if I had a lone pair of electrons from another molecule come in and interact with that hydrogen, okay? And so molecules like water, where you can have these types of interactions, form these networks of hydrogen bonds, okay? And this is what leads to the, the high boiling point of water. The molecular weight is 18, right? It's very low, but it boils at 100 degrees Celsius. The reason is that when you send water into the gas phase, you have to break up all of these H bonds, and that's going to cost you energy. And so hydrogen bonding is just a specialized case of a Bronsted acid-base interaction. Okay. When we talked about those interactions back when we did acidity, we said that, a Bronsted acid is any species that can donate a proton. A Bronsted base is any species that can accept a proton. And we drew that as, very generically, something like that, where I transferred that proton to the base. This is hydrogen bonding is just like that, except we're not doing the full proton transfer. So the proton is still bonding to its conjugate base. It's still bonding to A, but it's also bound to B at the same time. And so you get this weak bond because you're not forming a full bona fide bond. It's much weaker. H bonds are typically on the order of 4 to 11 kcals per mole. Okay, and so if you think about water on the on your coffee cup or whatever, it beads up. It forms if you look closely enough, it forms a three-dimensional. The drops of water are three-dimensional. If you've been in an organic lab or you've acetone, paint thinner, things like that, you'll note that drops of that are actually quite flat, right? Those things just kind of pour out and smear. And the reason water, maintains this three-dimensional shape is because of the H bonding. So if you start to pull it apart, you break the H bonding, that costs energy. So it's a lower state for it to kind of stick together, okay? All right, so just to give you some numbers to show why, how important this H bonding can be, we can think about some low molecular weight compounds. Okay, so methane, for example, has a molecular weight of 16 and it boils at minus 161 degrees Celsius. Ethane is 30 and that boils at minus 88. Fluoromethane is 34 and that boils at minus 78, okay? And then methanol is 32 and that boils at 65 degrees C, right? So you see the huge difference here. They're not quite equal in weight, but ethane versus methanol, you're talking about over 100 degrees Celsius, and part of that's dipole, but most of that is deriving from the hydrogen bonding, okay? And so, yeah, so that leads me to alcohols. I can just end by introducing methanol. So methanol is just replacing one of the hydrogens in water with a methyl group. Ethanol is replacing with 2 carbons. Okay. So ethanol is the alcohol you drink. Methanol is the alcohol you don't drink. And so back in the day, during Prohibition, when you couldn't get ethanol containing drinks, people drank methanol and then they went blind. And it was very unfortunate, but that's Darwinism at work. And I'll leave you with that. So I'm going to turn it off and then come back in about 5 or 10 minutes for office hours. All right.